In this paper, we propose a novel method that uses hierarchical graph neural networks to model garment dynamics in a generalizable way. Our method is able to generate dynamic motions for a wide variety of garment types, including free-flowing ones like skirts and dresses. In particular, our approach results in a single trained network that is able to generalize to novel garments not seen during training. Learning-based methods have recently demonstrated their potential to replace computationally expensive physics-based simulators. While these methods yield plausible results, they are limited in several ways. First, they are garment-specific. That means they can predict deformations only for the particular outfit they were trained on and cannot generalize to novel garments. Second, they learn the deformations as a function of the body pose and shape, which limits their ability to model free-flowing secondary motions that do not follow the body closely. Third, they are holistic models that cannot cope with changes in clothing topology. For example, zippers opening or buttons being undone. In this work, we propose to instead learn the local behavior of fabric. In this way, our method generalizes to arbitrary types of garments, including those unseen during training. Also, since our method does not rely on linear blend skinning, it can auto-regressively simulate loose free-flowing garment motions. Unlike state-of-the-art approaches, our local graph-based method can model garments with dynamically changing topology. And simulate different materials without retraining. Our work extends mesh graph nets in using a graph-based, message-passing neural network. Representing the garment as a graph, in each time step, we augment the graph with new edges between garment and body nodes based on spatial proximity. Run a fixed number of message-passing processing steps over the graph, and then generate accelerations for each node of the garment. Due to the fixed number of message-passing steps, a given signal can only travel across a fixed number of edges in a single time step. This limited propagation radius results in excessive stretching of the garments and implausible dynamics. We solve this problem by building a hierarchical graph with several levels of long-range edges and a multi-level message-passing architecture. This allows for a larger propagation radius and eliminates implausible stretching. We extend the physical objective formulation from snug with a novel friction term and train our model in an unsupervised way without the need for a time-consuming stage of data generation. We compare our method to state-of-the-art approaches by Santisteban et al. In contrast to these methods, our approach does not rely on linear blend skinning, and hence it's able to better model secondary motions of garments that do not follow the underlying body model closely. For example, the garment falls down under the influence of gravity when the person is upside down. Note that our results are generated with a single network, while the prior methods require training a new model for each garment. As our method does not rely on the overall geometry of the garment, it can generalize to a wide variety of garments. Here, with a single network, we model dynamics of all garments from the training set. Then, we modify the training garments to get 4 new ones. The same network can handle the modified versions as well. Finally, we use the results of the fold sketch method to demonstrate how our model generalizes to completely novel garments and create another garment, the long skirt, manually with Blender. The same network can model the novel garments too. Our method is also able to model garments with parts made of different materials. Here we dynamically change the bending coefficient of the shoulder patch to make it stiffer. This changes the wrinkles and dynamics realistically. We can manipulate the size of the garments at inference time to emulate tighter and looser fits. Notice how the wrinkles are influenced by the size of the garment. Our method can also model real-world garments. Here we manually extract the garment mesh from a 3D scan, and then simulate it using our model with default material parameters. To summarize, we present a novel method for modeling garment dynamics that can generalize to a wide variety of garment types including unseen ones, can model garments with changing topology, can handle dynamically changing materials and sizes, and is trained in a purely unsupervised way without any physically simulated data. Thank you for your attention.